Welcome to this explainer. Today, we are going to strip away the illusion of unprecedented magic and look directly under the hood of generative AI. If you've been following the tech space at all, you already know the headlines, right? You've seen the breathtaking outputs. But today, we're moving way past that surface-level hype. We're going to decode the foundational theory, the century-old history, and the actual practical mechanics of these creative machines. Look, for anyone working in or even just adjacent to the tech sector, understanding this stuff, it isn't just a curiosity anymore, it's absolutely essential literacy. Our goal right now is to figure out exactly what these systems do, what they definitely don't do, and how they actually work on a fundamental, mathematical level.
Here's our roadmap for today. We're going to hit 4 main stops. First, the new AI paradigm. Second, a century in the making. Third, the confluence, why now? And finally, the modality landscape. All right, let's jump right into Section 1, the new AI paradigm.
So, historically, artificial intelligence has essentially been a science of recognition and classification. Think about it. Given a piece of input data, the machine's job was simply to predict a label. It drew boundaries to tell us, hey, is this email spam or does this medical scan show an anomaly? It was all about identifying reality. Well, generative AI completely inverts that relationship. It moves from identifying reality to actually simulating it. Unlike older AI that just categorizes stuff that already exists, generative AI is a learned, productive, and probabilistic system. Instead of just mapping data to labels, it actually learns the underlying high-dimensional structure of the data itself. And it has to learn it well enough to create entirely new artifacts that have literally never existed before. Now, as you might guess, this is vastly more computationally demanding. It doesn't just flag a spam email, it writes a bespoke one. It doesn't just detect a tumor on an X-ray, it can synthesize a realistic, brand-new radiograph entirely from scratch.
To really wrap our heads around this, think of older discriminative models like a highly trained wine critic. The critic tastes a wine and, assigns it a score, or maybe categorizes its flavor profile. It takes a really complex input and reduces it to a simple output. But the generative model? That's the winemaker. To synthesize a totally new, highly plausible vintage, the winemaker has to deeply understand the climate, the soil chemistry, the grapes, the whole fermentation process, the whole shebang. The absolutely crucial point here is that producing something demands a vastly richer, more comprehensive internal model of the world than simply judging it does. To generate something that feels real, the machine inherently has to model the complex rules that govern that reality.
Okay, let's look at how this actually happens probabilistically. Imagine a tiny toy language that only has 3 words: sun, rain, and umbrella. If we feed our model a bunch of 2-word sentences from this little toy world, it learns that the phrase rain umbrella happens, say, 40% of the time, while sun umbrella only happens 5% of the time. Now, here's a really surprising fact. Underneath the seeming magic of today's incredibly fluid chatbots, there isn't actually a thinking brain. There is ultimately just a massive, incredibly complex probability table of words. The model isn't thinking in the way you and I do, it is simply sampling from a learned distribution to build plausible sequences. Now scale that idea up. Move from a 3-word vocabulary to a 100,000 token vocabulary. Replace that simple little table with a deep neural network containing literally hundreds of billions of parameters. Suddenly, that simple probabilistic sampling creates this absolutely stunning illusion of reasoning. Learn the distribution, then sample from it. That's the conceptual core of it all.
Moving right along, let's hit Section 2, a century in the making. Looking at this timeline reveals a pretty fascinating truth. The theoretical seed for generative AI is actually over 100 years old. Way back in 1906, mathematician Andrei Markov introduced Markov chains by analyzing the statistical structure of consonants and vowels in Russian poetry. Then jump to 1948. The father of information theory, Claude Shannon, literally used pencil and paper to calculate the probabilities of English letters. He built these crude models that could actually predict the next character in a sequence. Fast forward a bit, and we move through the connectionist revival in the 1980s with backpropagation, which allowed multi-layered neural networks to learn. By the 2010s, we hit the deep generative explosion with architectures like GANs. That's generative adversarial networks, which basically pit 2 networks against each other to create incredibly sharp synthetic images. And finally, the introduction of transformers in 2017 paved the direct road to the massive public deployment phase we're living through today. So you see, this absolutely did not just fall out of the sky overnight. It's been a slow, century-long evolution of applied mathematics.
But, this timeline begs a massive question. If Claude Shannon had the underlying statistical math all the way back in 1948, why didn't he build ChatGPT?
Well, that brings us directly to Section 3, The confluence. Why now?
The answer to that question really lies in a perfect storm. We are looking at a strict, multiplicative framework of three specific ingredients: data, compute, and algorithms. And it is absolutely crucial to view this as multiplication, not just addition. It's data times compute times algorithms. If any single one of these variables is zero, the entire generative AI boom we are witnessing right now simply fails to happen. Shannon had algorithms, sure, but his compute and data were basically zero. The 1990s had growing compute, but they completely lacked web-scale data and parallel processing architectures. It really wasn't until the 2020s that all three of these independent curves crossed critical capability thresholds at the exact same moment.
Let's break those down. First up, data. Because generative models learn incredibly complex distributions, they need massive amounts of samples to build accurate models of the world. In the 2020s, the internet matured into this vast, machine-readable archive of human knowledge. Projects like Common Crawl provided petabytes of raw page data. But here's the real structural shift: self-supervision. In the past, machine learning required humans to manually tag data. Think of explicitly labeling a picture cat. That human labeling bottleneck severely restricted the size of datasets. But through self-supervision, models learn by simply predicting the next word in a script document. The next word in the sequence basically serves as its own label. This brilliant little trick entirely bypassed human limitations, essentially unlocking the whole internet as a free, infinite training ground.
Second, compute. We're talking raw arithmetic firepower here. To process that unimaginable ocean of data and adjust billions of parameters, training a frontier model today requires up to 10 to the 25th power floating point operations. Just to put that into perspective, 10 to the 25th power is a number so staggering, it represents more computational operations than there are grains of sand on the entire planet. No way, right? But it's true. This astronomical workload drove a massive surge in specialized GPU data centers. We went from running models on single chips to these sprawling, distributed networks of tens of thousands of accelerators all working in unison. This unquenchable thirst for compute has quite literally turned silicon and data center energy grids into resources of major geopolitical significance.
Finally, algorithms. Because let's be honest, data and compute alone are just inert potential. You need breakthrough algorithms to actually convert that raw power into genuine capability. The 2017 transformer architecture was exactly that catalyst. Older recurrent neural networks process text sequentially, word by word, which, as you can imagine, created a huge bottleneck. Transformers removed that sequential limitation completely, allowing every piece of a massive sequence to be processed simultaneously. This is the exact breakthrough that made it economically practical to train at web scale across all those parallel GPUs. But wait, there's actually another layer to this: alignment. While transformers gave these models a massively powerful brain, it was alignment techniques like RLHF, that's reinforcement learning from human feedback, that essentially gave them manners. RLHF is what bridged the gap between a raw, chaotic predictive model and the genuinely helpful conversational assistants we all use today.
All right, let's move into our final section, Section 4, the modality landscape.
Now that we know how it works and why it exploded, we can map this landscape by output modality. And what's cool is that each one presents a really fascinating mini-narrative of new capabilities and unique limitations. Text is the founding modality, right? It revolutionized enterprise assistance and search, but it inherently suffers from hallucinations, those confident fabrications of facts which are just born from its probabilistic nature. Image generation relies heavily on diffusion models, pushing the boundaries of commercial art, but it introduces some intense scrutiny over artist copyright and the societal impact of photorealistic deepfakes. Audio models, they can synthesize incredibly natural, emotive voices from just a tiny 3-second sample, which places them squarely at the center of controversies over biometric consent. Video is basically the current frontier, demanding immense temporal coherence so that generated objects actually obey the laws of physics frame after frame. And then there is code. Code is fascinating because you can contrast the fluid, subjective nature of generating, say, a poem with the rigid, unforgiving logic of a script. Code executes, meaning its correctness can be mechanically checked. So every single modality here unlocks incredible economic efficiencies, but for sure they also introduce highly specific signature challenges.
But here's the thing, these modalities aren't just staying in their own isolated lanes anymore. We are rapidly converging on multimodal foundation models. These are systems inherently designed to see, hear, and speak simultaneously. I mean, you can show a model a photograph of a complex circuit diagram, ask it a question via spoken audio, and it will literally verbally explain the engineering to you. This matters immensely because the real world isn't just text. Grounding artificial language within visual and auditory perception is the absolutely critical next step.
It's building the foundational software substrate necessary for real-world robotics and autonomous agents that can actually navigate our physical environments.
So we've covered the fundamental paradigm shift from identifying to simulating, the century-long history of the math, the perfect storm of data and compute, and this rapidly converging multimodal landscape. But as we close out today, I want to leave you with a philosophical puzzle to ponder. If these models are fundamentally just running advanced mathematics to sample from a learned probability table, is that statistical novelty the same thing as true creativity? Does it even matter how the artifact is made if the end result is totally indistinguishable from human genius? It's a massive question, and one that will undoubtedly define the next decade of our relationship with this technology. Thanks for joining me on this explainer.